So in our last lesson, we finally settled Fermat's sum of squares theorem, and we followed that by discussing the law of quadratic reciprocity. We saw three different statements of the law of quadratic reciprocity and proved that each of those statements were equivalent to one another. And in fact, one of those statements was Euler's original conjecture from 1744. And when Gauss proved the law of quadratic reciprocity, it brought him instant fame, having been a conjecture that Euler had stated and many mathematicians had already tried to tackle in the time since. One of them being Legendre, who we talked about briefly. But Gauss's original proof was very technical and required lots of clever arguments to be able to prove the law of quadratic reciprocity, and Gauss was not entirely pleased, although he was still pleased with the fact that he was able to prove it, calling him his aurum theorema. But it was a result that he will come back to throughout his lifetime and find new proofs for it. And in fact, by the end of his lifetime, he had found 6 different proofs of the law of quadratic reciprocity. His simplest of the proofs was the one that he made in 1808, and it relied on a result that we call today Gauss's lemma. Of course, we need to be careful. Gauss has a lot of results associated to his name. And so whenever we are talking with questions pertaining to the law of quadratic reciprocity, Gauss's lemma is synonymous with the one that we will be discussing today. But even then, that proof was still very technical. It was the simplest of the proofs that Gauss envisioned. But the simplest of all the proofs out there is the one that we will be covering on Wednesday. And it is due to Gotthold Eisenstein in 1844. And so what Eisenstein did is that using Gauss's lemma as a thread, he was able to show that through Gauss's lemma and some clever arguments, we can translate all of these questions that we are looking at in terms of quadratic residues into counting lattice points in a triangle. And that's how we will be proving the law of quadratic reciprocity on Wednesday. So let us go ahead and get started. Let's go out through Gauss's lemma and prove it. But first we need a theorem, which essentially will be our building block to proving Gauss's lemma. So what does the statement say? So it says P is a knot prime, A bar is a non-zero element of the integers modulo P, and if we consider the list A bar times 1 bar, A bar times 2 bar, and we go all the way to A bar times P minus 1 over 2 quantity bar, then that list can be reordered into the list 1, 2, all the way to P minus 1 over 2 bar. But of course, that's not entirely correct. We need to ignore the sign of the elements. So what do we mean by sign? And so what this is saying is that if we look at this list and write that as J bar, we can go ahead and choose our J. If we don't care about additive inverses, we can choose that J bar to be between 1 and P minus 1 over 2. So another way of thinking about this is as in terms of absolute value. And so our book doesn't do this, but there are authors who talk about Gauss's lemma in the following way. So given a B bar in the integers modulo P, let the absolute value of B bar be equal to J bar, where J is between and 1 and P minus 1 over 2, and B bar is either equal to J bar or the additive inverse. And so we know that when we're looking at the list from 1 through P minus 1, the additive inverse of 1 is negative 1, which is P minus 1. The additive inverse of 2 is P minus 2. And so we know that we can always find, if we have B bar equals J bar, then it's either going to be J bar or the negative J bar for that B bar. Those are the two possibilities if we're restricting to those elements between 1 and P minus 1 over 2. And so we can define the absolute value of an element in the integers modulo P in this way. And so now with that language, what this is saying is if we consider the list A bar times 1 bar, A bar times 2 bar, all the way to A bar times P minus 1 over 2 quantity bar, if we take the absolute value of each of these elements, then we can reorder it to be this list here. And so that's another way of thinking about this statement and its phrasing. So let's go ahead and prove this. So we know from theorem 1.8.8 that if we have a natural number n and the integers modulo n, then the list of elements a bar times 0 bar, a bar times 1 bar, all the way to a bar times n minus 1, it contains every single element of the integers modulo n if and only if the GCD of a and n is 1. In our case, a is non-zero modulo p, and p is prime, so the GCD of a and p will always be 1 whenever a is non-zero modulo p. And so we have, by theorem 1.8.8, that we can rewrite the list. So by theorem 1.8.8, the list a times 1 bar. I'm just going to go ahead and write these down. And so we have this reordering. So this is just a restatement of theorem 1.8.8. We have our list all the way now to p minus 1 bar. We can reorder it so that it's 1, 2, all the way to p minus 1 bar. So next thing, now let's make the following observation. That if we have a times j bar, its additive inverse is going to be a bar times p minus j bar, because this is going to be a bar times minus j, because p is going to be 0, and so we have minus aj bar. So we have that the additive inverse of a times j is negative aj bar. And so as a consequence, what we can do now is, let's go ahead and consider k bar is equal to a times j. With k being between 1 and p minus 1. But now we're going to make the following note. To observe that either this is true just for any k. We always have that we're going to have 1 is less than or equal to k, less than p minus 1 over 2, or 1 is going to be less than or equal to p minus k, less than or equal to p minus 1 over 2. And so we always are going to have that one of these inequalities holds true, given the k being between 1 and p minus 1. But now if we couple this with what we have over here, for in terms of a times j bar, that its additive inverse is minus aj bar, where we have p minus j quantity bar, then we get, in particular, the list 1 bar, 2 bar, all the way to p minus 1 over 2 bar has a times j bar, or I should say k bar, or minus k bar, its additive inverse, appear exactly once. And that's what we want to prove, because our k is our a times j. So we have k is equal to a times j, but we know by the theorem that if we had a times k bar, where k is between 1 and p minus 1, that gives us the whole list from 1, 2, all the way to p minus 1. But now, we know that the additive inverses appear for 1, 2, they all appear in reverse, so 1 additive inverse p minus 1, 2 p minus 2. The difference is that now we have a times j, but we still know that a times j, its additive inverse is going to be minus a times j. And so if we omit this, if we ignore the signs as is phrased here in the earlier notation, then we know that this list here has to contain k bar or minus k bar exactly once, but we have only p minus 1 over 2 elements, so that shows that we can reorder the list in this way. And so that concludes the proof. And so now we are ready to prove Gauss's lemma. So here's Gauss's lemma, and we actually have already done the hard work. So before we state Gauss's lemma, let me just go ahead and go through this definition, which is what this book's way of talking about that absolute value I just mentioned. And so here we're going to have, we have P is prime, we have A bar as an element of the integration modulo P, that is non-zero mod P, and we have it being between 1 and P minus 1. Then we say that A bar is a negative residue if we have that A is between P plus 1 over 2 and P minus 1. So in other words, A bar is equal to negative K bar for some K between 1 and P minus 1 over 2. And similarly, we say that A bar is a positive residue if A is between 1 and P minus 1 over 2. So let's compare with what we have over here. If B bar is equal to J bar, where J is between 1 and P minus 1 over 2, then we say that it's positive, a positive residue. And if we have that B bar is equal to negative J bar, where J is also between 1 and P minus 1 over 2, then we say that B is a negative residue. And so Gauss's lemma does is give us a new way of computing the Legendre symbol by counting the number of negative residues. So specifically, we have that if P is a not prime number, and A bar is a non-zero element of the integration modulo P, and we let G be the number of negative residues appearing in the list that we just considered A bar times 1 bar, A times 2 bar, all the way to A bar times P minus 1 over 2 quantity bar, then A on P is equal to negative 1 to the G. So how do we prove this? Well, like I said, the proof, we have already done the hard part. So by the previous theorem, by theorem 1.17.2.1, we know that A bar times 1 bar times A bar times 2 bar times all the way to A bar times P minus 1 over 2 quantity bar. So A bar times 1 bar times A2 times 2 bar all the way to A bar times P minus 1 over 2 bar is going to be equal to this product. But not quite, because while every element in here appears in this list up to sign, what we have is that if this here appears to a negative sign, then we're going to have a negative 1 times P minus 1 over 2 bar. And then similarly a negative 2 bar if 2 occurs here as a negative. But now we can go ahead and count those negative residues. And so by that theorem, we have that this here will be equal to negative 1 bar to the G, since that is going to be the total number of negative residues that we have. And then the theorem tells us that the rest will now be the positive residues, 1, 2, and I misspoke, not the positive residues, but the 1 times 2 times P minus 1 over 2 bar. And so what we are simply saying is a restatement of the theorem. This here we ignore the signs. And so this is equal if we ignore the signs here. But if we do not ignore the sign, some of these are negative. So when we multiply them out, we're going to have a negative 1 to an exponent where now it's a total number of negatives that occur, which is what we are defining as G. So we have this equality here, but each 1 less than or equal to K less than or equal to P minus 1 over 2 is but each K bar with 1 less than or equal to K less than or equal to P minus 1 over 2 is a multiplicative residue. So in other words, it has a multiplicative inverse. So if we go ahead and multiply by their multiplicative inverses, so multiplying this equation here by the multiplicative inverses, gives the following. Well, we're going to have a cancellation. We're going to have that this A bar, this 1 bar will cancel off with that 1 bar, which is their own multiplicative inverse. But then 2 bar times the multiplicative inverse of 2 bar will cancel off also this one over here. And we continue in this manner. We multiply by the multiplicative inverse of p minus 1 over 2 bar on both sides. And that will get rid of this here. And so what we are left over is that on the left-hand side, we have a bar to the p minus 1 over 2. And this is equal to negative 1 bar to the g. But now by the equivalent conditions for modular arithmetic, we have that now negative 1 to the g, that a to the p minus 1 over 2 is congruent to negative 1 to the g mod p. But by Euler's identity, this is congruent to a on p mod p. And so we are done. We got our proof. We have now established Gauss's lemma, just like that. And so the thing with Gauss's lemma is that over here we will need to go ahead and find what the signs of each of them are. And so that may seem a bit counterproductive in terms of computing this, where here all we have to do is take a to the p minus 1 over 2. Not a great exponent in general, especially if p is large, but we can go ahead and then figure out what that is, what that's congruent to mod p. But the fact that we can count the total number of negative residues is going to have theoretical importance in the bridge that we are going to use via Eisenstein's lemma in the next lesson to prove the law of quadratic reciprocity. By far of the statements that Fermat conjectured in terms of which primes were sum of squares, the one that gave Euler the most trouble was the one of which primes occur as x squared plus 2y squared. And this was a result that took Euler until 1772 to prove. And his proof actually uncovered many of the things that would later become the foundations for Galois theory as well as algebraic number theory, and set the stage for the work in the 1800s on Fermat's theorem, which we will be covering starting in the 8th week of our course. And so right now what we are going to focus is on not on proving this statement from 1772, but asking when is 2 a quadratic residue mod p? And so that this question over here is interrelated with finding when is negative 2 on p is equal to 1. And so now we're going to go ahead and transition to looking at what is the quadratic character of 2. So we are not going to be proving the quadratic character of 2 in the way that Euler did. As I mentioned, Euler's proof had ideas and techniques that would later be generalized into Galois theory and algebraic number theory. And so that is beyond our scope for the course. But rather, we are going to prove this in the manner that Gauss later did, using Gauss's lemma. And here's where we get to see the technical marvel that Gauss's lemma does in aiding us to prove things like the quadratic character of 2, which took Euler almost 30 years to prove, and yet we can reduce it to a slide by means of Gauss's lemma. So how does the proof go? So let's see it. So first off, let me just say the statement. So we have p is a not prime. And what the quadratic character of 2 tells us is exactly when 2 is a quadratic residue mod p. And so what we have is if p is congruent to 1 or negative 1 mod 8, so plus or minus 1 mod 8, then 2 on p is 1. If p is congruent to 3 or negative 3 mod 8, then 2 on p is negative 1. So 2 is not a perfect square for p being plus or minus 3 mod 8. For homework, you will show that this statement here is equivalent to the following, that 2 on p is equal to negative 1 to the p squared minus 1 over 8. And so this will be question 4.19 in chapter 11. So now, let's go ahead and prove the quadratic character of 2. So here's the proof. So let us go ahead and consider the list. And so I'm going to label this star since we're going to be referring back to it. So we're going to do 2 bar times 1 bar, 2 bar times 2 bar, and we're just going to continue all the way until we get to 2 bar times p minus 1 over 2 bar. And now since we have that 2 is less than or equal to 2 times j, which is less than or equal to p minus 1, for 1 less than or equal to j, less than or equal to p minus 1 over 2, we have that there are, and I'm going to say this incorrectly, exactly half the elements of this will be positive and negative residues, but that's not entirely accurate because there is no guarantee that upon dividing p minus 1 over 2 by 2, so p minus 1 over 4, that is an integer. And so we have that there's going to be at most p minus 1 over 4 positive residues. So I'm going to go ahead and write this down. So note that about half of the elements in star are positive residues. And so I'm going to put this in brackets since this is technically not part of the proof, but just what I said verbally. And what we want to make sure is that we don't overshoot p minus 1 over 2 in this list, so specifically p minus 1 over 4. So we can only go as far as 2 times 1, 2 times 2, all the way to 2 times p minus 1 over 4 if that appears in the list. And so here, so since p minus 1 over 4 is an integer, if and only if p is congruent to 1 mod 4, we deduce that there are at most p minus 1 over 4 positive residues in the list star, and in fact there are the floor function, so the floor of p minus 1 over 4 positive residues. Now, the floor function, recall that this is the greatest, so here's the definition. So the floor of x is defined as the maximum integer k, such that k is less than or equal to x. But then, there are g, which is equal to p minus 1 over 2, minus the floor function of p minus 1 over 4, negative residues. Now, p is an odd prime. Since p is an odd prime, we consider the cases p congruent to 1, 3, 5, and 7 mod 8 separately. And so that's what we're going to do now. We're going to break this into cases, and then we're going to apply Gauss's lemma because now we know what g is. And so if we take negative 1 to the g, we can compute 2 on p. So let's go ahead and do this. So case 1. So suppose that p is congruent to 1 mod 8. So then p is p is equal to, then there exists some k, some integer k, such that p is equal to 8k plus 1. Then g, which is p minus 1 over 2, which is now we're going to plug in 8k plus 1. So we're going to have g is equal to 8k plus 1 minus 1 over 2 minus the floor function of 8k plus 1 minus 1 over 4. But now this will simplify to 8k over 2, so 4k, minus 8k over 4, which is 2k, but that's an integer. So that's just going to be equal to 2k, and so we get 2k. And then by Gauss's lemma, we have that 2 on p is equal to negative 1 to the g, which is now negative 1 to the 2k, which is always even, so it's always equal to 1. And so just like that, we just got this statement. And we are a quarter of the way there. So let's continue. So case 2. Suppose p is going to go into 3 mod 8. So then there exists some integer k such that p is equal to 8k plus 3. But then we have that g is going to be 8k, but then it's going to be plus 3 minus 1, so plus 2, over 2, minus the floor function of 8k plus 3 minus 1, so 8k plus 2 again, over 4. And so the first one is going to become 4k plus 1. But then we're subtracting the floor function of, that was going to become 2k plus a half. And so the greatest integer that we can have is going to be exactly 2k for the floor function. And so we're going to be left with 2k plus 1. And so that implies that the Legendre symbol of 2 on p would be equal to, by Gauss's lemma, to 2k plus 1, which is always odd, so minus 1. And so we get this here. And so that's negative 1, and now we got this statement for p congruent to 3 mod 8. And so I'm going to go ahead and now do the next two cases, and they're going to follow exactly the same way. So case 3. So here's the argument for case 3. Same as before, p is congruent to 5 mod 8. We have an integer k, so that p is equal to 8k plus 5. We now have that g is equal to this quantity here upon plugging in and simplifying. But then we will have that the Legendre symbol is 2 on p. By Gauss's lemma, we have negative 1 to the 2k plus 1, always odd, equal to negative 1. But 5, p congruent to 5 mod 8, that is the same as p congruent to negative 3 mod 8. And so we got that. So all that remains is to check p congruent to 7, which is congruent to negative 1 mod 8. And so I'm going to go ahead, pause the video, and do that right there. And so now here we have case 4. P is congruent to 7 mod 8. So p is equal to 8k plus 7 for some integer k. Then we can go ahead, substitute in for g. The floor function is now 8k plus 6 over 4. And so that's going to give us 2k plus 3 halves, but the greatest integer less than or equal to this is going to be 2k plus 1. And so that's what we have in here. And so we simplify this. We have 2k plus 2. That's always even. So by Gauss's lemma, this is equal to 1, which tells us that the Legendre of 2 on p is 1. And we are done. We have established the quadratic character of 2 in one slide, although technically 2 slides since I had to move things around. But just like that, we were able to prove the quadratic character of 2 using Gauss's lemma. And this is a vast improvement on Euler's original proof of the quadratic character of 2. To finish it off for today, let us revisit Euler's result from 1772. And now that we know the quadratic character on 2, let's go ahead and find what are those primes for which negative 2 on p is equal to 1. And what we will show is that negative 2 on p equals 1 if and only if p is congruent to 1 or 3 mod 8. And so here's the fascinating thing from a historical standpoint. In our course, we proved from awesome of squares theorem. And we did this by doing the descent lemma and the reciprocity lemma. Our reciprocity lemma, the proof of it was just quite short because we had all these theorems. We knew that the quadratic character of -1 on P already. And so we had a very short proof. But as I mentioned, this is what caused Euler the most difficulty to do. The descent lemma, while for us, it makes, at the first doing, it is a very clever argument. The process by which it's done generalizes to the case where you're looking at those primes that divide x squared plus ny squared with GCD of x and y equal to 1. And so Euler was able to do a descent lemma for the case of 2 and for 3, and so that did not cause him difficulty. And if you're curious on investigating this further, one of the projects does look at Euler's proof in the case of 3. And the descent lemma is going to follow for that case similar to what we did. Clever, but the same argument essentially. Euler, the hard part for him was establishing the reciprocity step. And so specifically, when is -2, for what primes do we have the -2 on P is equal to 1? But now that we have the quadratic character of 2, we can get it. And that was the hard part for Euler. But now we can go ahead and compute this in one slide. So here it is. We're computing -2 on P by the multiplicativity of the Legendre symbol. This is -1 on P times 2 on P. Now, this is equal to 1 if and only if -1 on P is equal to 2 on P is equal to 1, or -1 on P equals 2 on P is equal to -1. But now, -1 on P is equal to 1 if and only if P is congruent to 1 mod 4, and 2 on P is equal to 1 if and only if P is congruent to 1 or -1 mod 8. And so this is the first part. I'm gonna put it in brackets so we have the if and only ifs. Easier to read. And then for the next part, we have -1 on P is equal to -1 if P is congruent to 3 mod 4, and 2 on P is equal to -1 if P is congruent to 3 or 5 mod 8. And so we have this here. But now, if we look at this here, P is congruent to 1 mod 4, and P is congruent to 1 and 7 mod 8. The only way that this here is a valid statement is if P is exactly congruent to 1 mod 8. Because if P is congruent to 7 mod 8, then P will be congruent to 3 mod 4. And so then we have that this here, the first one, just reduces down to P congruent to 1 mod 4, or, to 8. Or, now we look at the other one, we have 3 mod 4 and 3 and 5 mod 8. But 5 mod 8 is 1 mod 4, so the only possibility is 3 mod 8. And so we are done. We now have our string of equivalences, and just like that, we have established that portion of what would be the reciprocity lemma of Euler's from 1772, which, coupled with his descent lemma, which he had already done 20 plus years prior, he was able to prove that statement of which primes are exactly of the form x squared plus 2y squared.